Hey there. Oh, lost it. There we go. Lesson 7. Okay, the goal with Lesson 7 is learning to interpret a negative exponent in equations that represent exponential growth or decay. So we're dealing with some negative exponents. Let's get into our little warm-up. How would you rewrite each of the following as an equivalent expression with a single exponent? All right, we've learned in the past. Oh, my tablet's not awake yet. We've learned in the past that if we have, come on, there we go. Because we have 2 as sort of the base for both of these, hold on. My tablet was not connecting. There we go. I don't remember what I was saying, but if I have 2 as a base, they're the same, I can add the exponents. Basically, x to the a times x to the b equals x to the a plus b. You learned this in pre-algebra, right? So we're reviewing it right now. So this would be 2 to the 4th power. Here we have 4th and 2 to the negative 1. So it's 2 to the 4 minus 1, which is 2 to the 3rd power. Again, 2 and 2, so I add the exponents. 2 to the 4th, I guess I could say plus a negative 3, which is 2 to the 1st power. And then 2 to the 4 plus a negative 4, which is 0, 2 to the 0 power, which is 1. All right, so this is really 4 plus 0 to keep my notation the same. And this should be plus a negative 1. It's the same thing, but I know that's going to confuse some of you. So that's where we are. All right, moving on. So a marine biologist estimates that a structure of coral has a volume of 1,200 cubic centimeters, and that its volume doubles each year. That's amazing. Okay, so its initial volume and we are doubling each year. So we've learned how to write these equations. Basically, we would have, I don't know what variables to use yet. So right now I'm going to do initial volume times 2 to the t, all right? And here it says in number 1, write an equation in the form y equals a times b to the t, representing the relationship where t is time in years. Okay, sorry. A is your initial amount, which in this case is 1,200 centimeters cubed. We are doubling, so it's times 2 to the t, all right? So A is your initial amount, and B is your factor. All right, find the volume of the coral when t is 5, 1, 0, negative 1, and 2. So let's do TV, 5, 1, 0, negative 1, and negative 2. Okay, need my calculator. So I'm typing in 1,200 times 2 raised to the 5th power. Pretty big number. 38,400 cubic meters. Now we do the same thing, but it's 1,200 times 2 raised to the 1st power. That's just doubling, 2,400. T raised to the 0 power. Now t raised to the negative 1. 1,200 times 2 caret negative 1. 600. And 1,200 times 2 raised to the negative 2. 300. And these are all cubic meters, right? Centimeters, cubic centimeters. Okay? Now, What does it mean in this situation when t equals -2? Okay, well, t equals 0 is your initial time. Initial, I can spell, we're good. Initial time when we're at 1200 centimeters cubed. So time equals -2, you're going backwards, okay, 2 years. So time equals -2 would be 2 years before the reef was measured at 1200 centimeters cubed. So 2 years prior to your initial time, okay? So 2 years before your initial amount, your coral reef was 300 centimeters cubed. And then it grew to then it doubled to 600, then it doubled to 1200, then it doubled to 2400, and then, okay. In a certain year, the volume of the coral reef is 37.5 cubic centimeters. Which year is this? Explain your reasoning. Okay, so if we know the volume is 37.5, and the initial amount was 1200 times 2 to the t, we're trying to figure out what year this was. Okay, well, when you get to Algebra 2, we will teach you how to solve this algebraically. But right now, you don't know how, all right? So we're just going to figure it out. So if I try, we already tried t equals -2. So let's try t equals -3. That's going to be a volume of 150 because it's half of this. And then t equals -4. That's going to be a volume of 75 because it's half of the 150. T equals -5. And there we are. My volume is 37.5. And I could type that into y equals 1200 times t to the -5 to double check. And that does in fact equal 37.5 centimeters cubed. Okay, windows of graphs. The volume y of coral in cubic centimeters is modeled with the equation y equals 1200 times 2 to the x, where x is the number of years since the coral was measured. 3 students used graphing technology to graph the equation that represents the volume of coral as a function of time. So here we have just 2 points. Look at that. So our initial value is at 1,200 and half of that. Okay, here, I can't even tell what's going on. We're so close to the x-axis, but then we exponentially grow. And then here, looks like I see a better, like year 1, 2, and 3, I can actually read something, versus here, year 1, 2, and 3 all look very equal to me. And here, we don't even have years 1, 2, and 3. This is interesting. All right, let's look at the problem. Describe how well each graphing window does or does not show the behavior of the function. Okay, I just talked about it a little bit. If you look at that graph, like what are we looking for? Here I've got year prior to measurement. I can read it. The year of measurement, I can read it. But I have no idea what's going on in years 1, 2, 3, or 4. Okay, so it's not very useful. Because why? Well, I need my y-axis to be much bigger. I need my y-axis to show more data. Okay, if I look at B, years -1 to 3, they look equal. And we know they're not equal. Okay, so this one's also not useful. Oops, not useful. I don't know. So for graph A, where we needed the y-axis to be more, in graph B, we really need the y-axis to be less. Okay, it goes all the way up to, I don't even know what that is now, 100,000 or 1 million. Okay, it needs to be much smaller. Okay, it's not useful. So B, we need the y-axis to show less, data. And then C, if you look, like -1, I can read it. 0, pretty well. 1, 2, 3, 4, 5. I can read all data points. Okay, I'm going to make some assumptions down here. I'm going to estimate. It's probably better than writing assume. I can estimate those smaller ones much better than I can here. And I can read pretty well. Not so bad. So C looks good. Okay, my X and Y axis show the data pretty well. Right, for each graphing window you think does not show the behavior of the function well, describe how you would change it. For A, I would make the y-axis go from 0 to a larger number. Okay, that's definite. The x-axis, you could change it. I don't think you necessarily need to. You could increase the maximum if you wanted to. With B, you want the y-axis to go from 0 to a much smaller number. And the x-axis, I think, is good. Make the changes you suggested and sketch the revised graph using graphing technology. If we did this, if I changed A and B, it would look like C. Okay, my goal is to make A and B look like C. Okay, one more example. This is our lesson that has 4 student task statements. A person took some medicine but does not remember how much. Concerned that she took too much, she has a blood test every hour for several hours. Time T is measured in hours since the blood test, and the amount of medicine in her body, M, is measured in milligrams. What is the growth factor? That is, what is B in the equation in the form of M equals A, B to the T? Okay, and what is A? So A is your initial amount. We can say A in this case is at time equals 0, 100 milligrams. B, we need to find. Okay? So I know as time goes on, it looks like I'm going down by half. If I did 50 over 100, that's 1/2. If I did 25 over 50, that's 1/2. So that equals B. So M equals 100 times 1/2 to the T. Find the amount of medicine in the patient's body when t is -1 and -3. So m equals 100 times 1/2 to the -1. M equals 100 times 1/2 to the -2. So that means I'm going to have 200 milligrams and 400 milligrams because we're doubling the other way. Okay, I can check it on my calculator really quick. 100 times, I put parentheses, 1/2 raised to the -2, and I get 400. 100 times, parentheses, 1/2 raised to the -1, 200. We're good. Okay, what do t equals 0 and t equals -3 mean in this context? Well, when t equals 0, that shows the initial amount of medicine the first time it's tested. And then when t equals -3, let's see, t is measured in hours since the blood test. So that would be 3 hours prior to the first test. The medicine was taken when t equals -5. Assuming the person did not have any of the medication in her body beforehand, how much of the medicine did the patient take? So we wrote an equation. I can just use the equation. I don't have to do t equals -3, -2, -3, -4, -5. I can just use the equation. And when I type this into my calculator, that's exactly how I type it. Well, I use the multiplication button. Okay, actually, to tell you exactly how I type it, it looks more like this. Caret. 100 times parentheses 1/2 raised to the -5. (3,200 milligrams). And then plot the points whose coordinates are shown in the table. Okay, if I can do that. At 0, I'll just eyeballing it, literally. Okay, at time equals 0, let me change colors. We are at 100. Time equals 1, we're at half that. About 50, about 25, we're pretty close to 0. -1, we're at 200. -2, we're at 400. -3, we're at 800. Okay? That's it. Based on your graph, when do you think the patient will have 500 milligrams left in their body? There's 500. If I sketched a graph down here, somewhere between 2 to 3 hours before the test. Okay, about right there. Closer to -2 if you get exact, but, and then no medicine in the body? Goodness, at 3 hours, did you have that in the table? So at 3 hours, we're at 12.5. At 4 hours, we're at 6.25. At 5 hours, we're at 3.125, 6 hours. Can't do that kind of division in my head anymore. 1.56, right? We're at about 0. So that's 6 hours, 7 hours, 0.78, etc. I just keep on cutting it in half and cutting it in half. So I would say sometime after 10 hours. And I'm going to support that with the equation. (100) times 1/2 raised to the 10. And I get 0.0977 milligrams. Milligrams, right? Yep. Cool. All right, are you ready for more? This one's really fun. Okay, without evaluating them, describe each of the following quantities as close to 0, close to 1, or much greater than 1. Okay, you could email me. Oops, email me. Lesson number, okay, and the are you ready? Just so I know what I'm looking for. All right, good job today.